Good evening, everybody. Welcome to our presentation on hypersonic missile defense, stopping the unstoppable. So my name is Aaron Kennedy, and as Bernard said, I'm a graduate engineer to Lockheed Martin. And tonight I've got Jacob and Daniel, who also worked with or we worked collaboratively with this for the project on nuclear issues that we presented in June this year. So tonight we're going to give a brief overview on hypersonics for the benefit of the room, and also on lasers as well, and their feasibility as a solution to counter the emerging hypersonic threat from near peers. And this started as an idea that came from a piece in the literature done by the China Aerodynamics Research and Development Center, and they looked at this laser hypersonic vehicle coupling that you get, a coupling between the laser radiation and aerothermal heating that you get from a hypersonic vehicle during flight. And they predicted an increase in the ablation rate. And so we looked at this, looked at modeling a high level, similar scenario using similar principles to see really generally as a solution if this is a good one, if it's feasible. And so tonight we're going to be going through some of our results and also discussing some of the limitations of our modeling as well. So first of all, we'll start with what is a hypersonic vehicle. So generally, the rule of thumb is that hypersonic flight is defined at Mach 5 and above. And there are two main types of vehicles that we're talking about here when we relate it to hypersonic weapons, mainly HGVs or hypersonic glide vehicles, and also cruise missiles. So in this scenario that we modeled, we assumed a simplified glide vehicle, and such glide vehicles have been stated to be possible of achieving speeds of around Mach 27 in the press. For reference, cruise missiles or hypersonic cruise missiles in the range of Mach 5 to Mach 9. And one of the really concerning thoughts about these new weapon systems is that they're capable of carrying potentially nuclear or conventional payload. So we're looking at a new delivery mechanism with WMD type destructive capabilities. So what really is the issue? So the bottom right hand diagram here, you can see comparison of typical glide vehicle trajectories compared with cruise missiles and ICBMs. So it's kind of clear that the ICBMs shown by the white line follow quite a nice predictable ballistic trajectory that can be intercepted, whereas the glide vehicles highlighted by the red line never actually leave the atmosphere, typically operating between 40 to 100 kilometers. And so this allows them to maneuver throughout, take control or take advantage of the atmosphere to maneuver around conventional ballistic missile defense systems, or give them the potential to do this. So this could be a bit of a problem, as it's less predictable and gives you a greater challenge to try and counter it. So we mentioned that they're pretty fast, but how fast really is fast? So this is quite a nice graphic that puts the hypersonic speeds into perspective, in hopefully in terms that we can understand. So consider a commercial jet like you'd go on holiday to Spain with, or not at the moment, but in 30 minutes you could take you 370 miles while it's traveling at 500 miles an hour. Even faster, quite a famous Lockheed Martin aircraft, the SR-71, could travel at 2,200 miles an hour and could achieve about 1,268 miles. So blowing these out of the water is a vehicle called the HTV-2. This was a test development hypersonic glide vehicle, which could achieve speeds at approximately 13,000 miles an hour, and in this same time period could achieve over 8,000 miles. So this kind of puts into perspective the kind of speeds that we're potentially talking about here, and this is a problem. So we talked about hypersonic vehicles, but what is a laser? So a laser, for those of you who may not know, is actually an acronym, or started as an acronym, and stands for the light amplification by the stimulated emission of radiation, which is a bit of a mouthful. But essentially what it is a tube or a cavity with a medium in the middle and two reflecting mirrors on either side, with one partially reflecting. So what we do is we add energy into this medium, or we do what's called pumping the laser. And this excites some of the atoms, and in this excited state you'll get a few stimulated emission of radiation as the atoms want to reduce down to their ground state. So these photons emitted inside the cavity will then start to traverse up and down, being reflected between the two mirrors, and on their way past other excited atoms, they actually stimulate some more emission of photons, and then eventually you get a nice build-up of photons, and out the partially reflecting mirror you get a monochromatic coherent light beam. And what we're looking at is using this laser, or this coherent beam of light, as a delivery mechanism to deliver excess heat energy to the shields or to the heat shields of a hypersonic vehicle. So Jacob, if you'd like to take from here.
So when considering the use of lasers to attack hypersonic missiles, it's useful to chart the extent of their current use on the battlefield or in trials. The most recent example of this is the USS Portland, which is published online. Here, a 30 kilowatt laser fired at and neutralized an unmanned aerial vehicle during a test off the coast of Hawaii. Operationally, it works just a lot like a laser pointer, much more like a beam of focused sunlight from a magnifying glass than the repetitive shots seen kind of echoing out across the galaxy in Star Wars. It's been described by operators as extremely accurate. For example, if you're looking at a boat coming in over the water, you can target and take out the engine and not necessarily anything else. This kind of precision is something you don't get with conventional weapons because there tends to be much more collateral damage. The laser used was a Mark II version of the US's laser weapon system demonstrator, and is the first evidence of system-level integration of a high-energy laser across the US forces. Helios is another laser in development with the US Navy. This combines a laser with a counter-UAS dazzler alongside intelligence, surveillance, and reconnaissance features, and is scheduled to be field tested in early 2021. Next slide, please, Alan. Great. So in the land-based sector, a number of vehicle-mounted technologies are purported to enter service in the next decade. Very simply, these constitute placing a high-power laser and generator on a forward deployable truck. The generator and battery then provide the enormous peak power and thermal management needs for as long as fuel can be supplied. The power demands are so great that Rolls-Royce has adapted helicopter turbines for the task. The most interesting of these platforms is the high-energy laser tactical vehicle, projected to operate in the 250 to 300 kilowatt range. Its mission will be to protect against indirect fires, which are projectiles aimed and fired without a line of sight to the target. 4 such vehicles are expected to enter service in 2024, following full system testing in 2022. The upper limit of its estimated power is supposedly just enough to engage cruise missiles. So just to summarize the near future laser deployment, at present, there seems to be a proven capability to attack individual UAS systems with a likely capability to defeat swarm UAS attacks, which within the next 5 years is likely to broaden to encompass indirect fire protection too. But it does remain to be seen how effective laser technology could be against future threats such as hypersonics, and hopefully we come to address that later in the presentation.
Cool, so we've heard there about some systems that are currently in development and also in use at the moment, but mainly they're based on counter unmanned air systems and maybe looking at projectiles. But our target is looking at hypersonic vehicles, and usually this is accompanied by a thermal protection system to protect the vehicle during flight from the hostile thermal environment. So we can't just apply the same principles to as you would apply to unmanned aerial vehicles, for instance. So here we drummed up a couple of potential methods or kill mechanisms that we could look at. And firstly, we were looking at the laser invoked change to the geometry of the vehicle. So assuming an ablative TPS, you would lose material on the outside through flight. So we're looking at a local solution delivering excess energy to a local spot within the vehicle. And this has the potential to increase ablation, either through either directly through the increased heat energy at the surface, or potentially by changing the surface roughness locally. So if you can change the surface roughness locally and maybe transition into some local turbulent spots, then that would also give you an increased heating at a point or within a local area on the vehicle. And this could eventually lead to some asymmetry during flight. So what we're doing here is changing the vehicle geometry on one side, and this will change the aerodynamic forces also working on the vehicle and has the potential to cause it to veer off course towards the target and maybe even prevent it from maneuvering back on to target. So we're hindering its capability to maneuver in flight. A second kill mechanism that was thought of is more direct, but it's by forcing the structure to operate outside of its design limits. So the idea of the TPS is to protect the structure during flight, but by increasing the heating by adding extra laser radiation or thermal radiation via a laser, we're essentially overloading, or we can think of overloading the heat shield capability by decreasing the effectiveness of the heat shield. So this increase of heating will eventually follow through to the substrate, which could induce a material property change, and so like a reduction in yield stress, for instance. And this structure will be weakened whilst being subjected to large aero forces. So what we're saying here is that the structure will be heated, there'll be a reduction in yield stress, and the material's ability to cope with the forces and the stresses during its flight will be diminished. So we could see the vehicle potentially breaking up during flight. So that's what we're looking at now. And so next we'll be looking at the modeling that we looked at.
Yes, thank you, Aaron. So yeah, obviously the paper written by the China Aerodynamics Research and Development Centre included calculations on the increased ablation rates that could be achieved by targeting a HGV with a laser. In order to make comparisons against, it was decided that we would create our own model of a HGV and simulate the effect of a 100 kilowatt laser incident on its surface before analysing the difference between the thermal environments, both with and without the laser effects. Prior to this research, none of us had experience modelling HGVs or their flight. We were able to use Lockheed Martin UK AMTIL proprietary code called FIRST 3D, or F3D for short, to complete our simulations. F3D is in essence a 6 degree of freedom solver which allows aerodynamic coefficients to be calculated and thermal environments to be predicted of objects thereafter. It's worth noting this modelling is not exhaustive, partly due to the limited time that we had available to us. In order to simulate the effect of laser, it was decided that we would add it as an additional heat flux term. Following the simulations, the predicted thermal environments of the HGV, both with and without the laser incident upon it, were compared to investigate the effect of its thermal protection system's ablation rate and the body temperature as a whole. Next slide, please, Aaron. HGVs don't always take a standard trajectory, as Aaron's already touched on when we looked at the trajectory and path of it. However, for the purpose of modelling, a simple glide trajectory was generated and used. Some basic assumptions based on a perceived operating environment of a HGV were made. As such, our HGV was set with an initial altitude of 70,000 metres, an initial velocity of Mach 18, which at that altitude is approximately 5,600 metres per second. The HGV was given an angle of attack of 20 degrees as well. It was assumed that the laser would be able to target the HGV when it came within range of current missile defence systems, such as PAC-3, at approximately 30,000 metres. The assumption was also made that the laser had an uninterrupted view of the HGV as it proceeded through the mesosphere, stratosphere, and troposphere from the point of which it was targetable. Some basic calculations yielded an 84-second illumination time for the laser on the HGV. Next slide, please, Aaron. So the graph we see there indicates the effect of the added heat flux from the laser on the temperature at a midpoint of the HGV's body. The temperature at the midpoint without the laser effect is indicated by the solid black line, whereas the dashed line indicates the temperature
at the midpoint with the laser effects. It can be seen that the additional heat flux from the laser significantly increases the HEV's body's temperature, in some cases by over 1000 Kelvin, and almost doubles it for the duration of the laser illumination, as indicated by the shaded grey area to the right of the graph. Our modelling suggested that the most effective point to impose the laser upon the HEV would be at the peak thermal stress, as can be seen in the graph shown. Next slide, please, Aaron. So the graph on this slide looks at the ablation rate. It shows the effect of the laser heat on the ablation rate of our HGV. It's the thermal protection system at the stagnation point, it should be said. The percentage increase the ablation rate is plotted against time, and we found that on average, the ablation rate of the thermal protection system was increased by 39%, which is indicated by the horizontal dashed line. The paper presented by the China Aerodynamics Research and Development Center suggested that they were able to achieve a point percentage increase of over 60%, indicated by the fine dashed horizontal line towards the top of the graph. However, the paper was unclear on the assumptions used, but we can draw some positive inference that our peak point percentage increase was approximately 50%. Another point of note is that the additional laser effect eroded the thermal protection system material, which in the case of the model was assumed to be carbon-carbon, within 30 seconds of it being illuminated, which highlights the potential benefits of using a laser to defeat a thermal protection system. Now, as I said, this modelling was not exhaustive, and there are some limitations to it, which Aaron is going to talk through.
Yeah, so as Dan mentioned, there were some limitations that we thought we should highlight. So, for instance, the additional heat flux term that we assumed from the laser, we assumed it to be 100% incident on the surface. So, in other words, ignoring any atmospheric effects from the laser radiation propagating through the atmosphere to the target. Also, we used a fairly simple glide trajectory, which doesn't account for any sort of maneuvers that one might expect, or any type of glide trajectory such as a skip glide shown in the picture below. Also, we assumed the TPS to be ablative, but this is not necessarily going to be the case. So there are other TPSs that could exist that we've grouped in either cooled, hot, or insulated structures. And it's also worth noting that there's a lot of research in this field at the moment looking for new innovative materials to increase the capability of thermal protection systems. So we're going to go through, for the benefit of the room, some typical thermal protection systems that exist in theory, starting with the cooled structures. So these can be thought of as active cooling systems that maintain a structure's temperature. So in the top left-hand side, you can see an example of convective cooling. And these have examples such as in rocket bell nozzles, where they've been used before. So in this instance, you have a hot gas or hot environment impeding on your structure, but you run a cooling fluid just below the surface. So the heat is conducted through the metal and then convected into your coolant. And then the coolant is pumped away to another part of the body. Sometimes this could be fuel, and then used to preheat the fuel before injecting into the nozzle. So yeah, that's one method. Another method is transpiration cooling. So this is in the bottom left-hand diagram, and this can be thought of similar to sweating. So again, you have a coolant below your surface structure, and as gas or the hot environment is impending on the surface, your coolant actually leaks through your pores onto the surface to actively cool your structure, so giving it some protection analogous to sweating. And thirdly, we have film cooling, which is shown in the bottom right-hand diagram. So this is kind of similar to transpiration cooling, but instead of having lots of pores where your coolant's leaking out onto the surface, you have a single discrete source upstream where coolant or a fluid is being pumped out, which creates a thin insulating jacket across the surface of the wing or surface of your structure. So there are others. Jacob?
Thanks, Aaron. So hot structures depend upon the conduction and radiation of the thermal energy away from the shell to maintain a balance with the thermal input. This makes them passive and they tend to be shape stable. It's typically used for moderate heat fluxes for relatively short times. It's only so long before the structure becomes too hot for the contents to survive. On the left, a thin layer of insulation is here that is on the left that the insulation structure uses a thin layer of insulation. Here, some thermal radiation away from the heat shield is the main mechanism used to remove heat. This type of heat shield was used for the elevons of the space shuttle. On the right, the main structural body absorbs the heat, becoming what is naturally called a hot structure. Although this is obviously untenable for long time periods, some heat is still radiated away from the vehicle. And the more heat that can be radiated away, the longer the vehicle will be able to withstand the heat flux. The leading edges of North American's X-15 hypersonic rocket-powered aircraft made use of this method to reach almost Mach 6. Next slide, please, Aaron. Brill. So an ablative insulating structure simply prevents surface heating from conducting too far into the vehicle and causing too much damage. Whilst passive and semi-active shields tend to be shape stable and can be reused, ablative heat shields perish and degrade as they re-enter, which limits their flight time. Ablative, however, can withstand higher heating loads and so is favoured for higher velocities and lower altitudes. As a result, ablative heat shields are the most relevant to hypersonic technology. So how do they work? The chief characteristic of re-entry aerodynamics is that the temperature of the flow is so great that the chemical bonds of the diatomic molecules of the air are broken. When the molecules break apart, they produce an electrically charged plasma that surrounds the aircraft. The heat shield must be able to withstand this. A common ablative material is carbon phenolic resin, essentially a carbon fiber weave fully impregnated with phenolic resin. Phenolic resin is an aromatic polymer chain of phenols bonded to hydroxy groups. And when exposed to atmospheric entry heating conditions, this material will partially burn to a char and reject heat via the following mechanisms. Firstly, part of the heat flux is transferred inside the heat shield. The virgin material thermally decomposes via pyrolysis and ablation. This pyrolysis carbonizes the phenolic resin into a low-density porous char, losing up to half its original mass due to the vaporization of the resin into the resulting pyrolysis gases. These gases are subsequently convected out of the material and exhaust into the gas stream, providing a further barrier for the heat exchange. Finally, ablation of the remaining carbonized resin and carbon fibers, otherwise known as the char layer, is promoted by further heterogeneous reaction of the gases. Phase change is also thought to occur alongside the mechanical erosion of the heat shield. The net effect is that all of this leads to surface recession and the gradual shape change of the vehicle. An example of a carbon phenolic ablative heat shield is that used by the Curiosity rover landing vehicle in 2012. This consisted of phenolic impregnated carbon panels patched together in a dome shape. Thanks, Aaron.
Cool. So we've now heard of some more thermal protection systems, and we mentioned that this could be a limitation of our modelling. However, we can look at this another way. So hypersonics at the moment are, or can be thought of to be, operating at the limit of the technology that's available at the moment. And so with a desire to keep both mass and cost of systems quite low, they'd likely have quite strict design parameters. So even by adding just a small amount of excess heating, either with a laser or by another method, we could actually apply this system to different types of TPSs, because with the intent of overloading the amount of heating that you have on the material, so overwhelming its ability to deal with excess heat. So actually, even though we have suggested that this is a potential limitation, actually that's likely not to be the case. However, one potential limitation of this laser-based solution is atmospheric effects, and we will be discussing that now.
There's a number of atmospheric effects which is likely to impact and severely hamper the amount of laser radiation that actually gets to the target. These are molecular absorption, molecular and aerosol scattering, atmospheric turbulence, thermal blooming, and installation local gas effects. So how does where the laser is situated or where the target is situated actually affect the amount of laser that gets there, the amount of photons that reach the target? Next slide, please, Aaron. Great. So work at the Naval Postgraduate School has gone some way to quantifying atmospheric effects. The graphs here show irradiance on the vertical axis, plotted against the wavelength of the beam used on the horizontal axis. The lighter colours represent an increase in the variable being studied. For example, on the first graph, light blue represents a more turbulent scenario than the dark blue outline. The horizontal orange line is a guide to the melt threshold, i.e. the minimum on-target irradiance required to melt a certain volume of the target material in a 10-second dwell time. Chart number 1 makes it apparent that turbulence in the air between the source and the target will hamper the irradiance. And turbulence comes from two key sources, atmospheric and installation. Atmospheric turbulence occurs as a result of fluctuations in the refractive index of the atmosphere. Less dense air has a smaller refractive index than more dense air, and so differential heating of the ground results in rising convective scales, and thus a fluctuating refractive index. Installation turbulence comes from the mixing of hot exhaust gases with cooler ambient temperature, with cooler ambient atmosphere, and which can be disruptive to the beam. Compression or expansion of the gas flow around the beam director, if it was mounted on a high velocity vehicle, for example, can disrupt the beam further. An example would be mounting the laser on the front of a plane. Combining these effects, to the naked eye, the target would appear to distort and shimmer in the sky. To the laser, these interferences severely disrupt the beam intensity. The center of the beam shifts, and the spatial profile of the laser beam is also extended, reducing the peak intensity. The precipitation chart shows that a successful engagement is unlikely for even the slightest amount of precipitation at a 5-kilometer target range. Extinction of the beam is a result of photon absorption by species in the atmosphere combined with the scattering of the beam by water molecules and other particles. Scattering by fog and clouds is particularly intense because the size of the droplets extends from 5 to 50 micrometers, which is particularly comparable to the beam wavelength. Absorption of the photons can lead to a phenomenon called thermal blooming. More energy is absorbed along the center of the propagation path, which reduces the refractive index preferentially along the propagation axis. This change in the refractive index across the width of the beam creates a lens, thereby focusing or defocusing the spot size. Both absorption and scattering of the beam ultimately lead to a reduction in the power density at the target area. The third and final graph naturally shows that range naturally negatively affects the irradiance. This plot shows the distance from 1 kilometer all the way up to 7 kilometers. Fundamentally, there is just more matter between the source and the target. All manner of scattering effects may limit the reach of the beam. Thanks, Aaron.
This naturally begs the question, how can we reduce atmospheric interference of a laser and increase its effectivity in turn? Well, one possible solution, as Jacob briefly touched on, is an airborne-based laser system. Typically, this consists of a laser mounted on an airborne platform which can provide air-to-air, air-to-earth or air-to-space capability. In comparison to current airborne weapon systems, the laser has no need for reloading in the same way as kinetic weapons such as guided bomb units or air-to-air missiles. Assuming the target to be a HGV or other airborne object, this also reduces the range of the laser to the target, which in turn reduces atmospheric propagation. The other added advantage of an airborne laser system is that it can operate above weather systems, reducing the impact of any additional atmospheric effects that Jacob discussed. However, an airborne laser system still sits within the atmosphere and will still therefore suffer effects, but on a lesser scale. It's also likely that an airborne laser system will take Sorry, just got a bit of background noise there. It is also likely that an airborne laser system will take time to become airborne or get to a suitable destination where it can be used. Due to the sizable power supplies laser systems currently require, it often means that the platform is slow and heavy, making it a vulnerable target to current defense systems. Due to the early development status of airborne laser systems, there is also very high costs associated with them. As you can see on the slide, an example of an airborne laser system was the Boeing YAL-1 project, started in 1996 in the US. This features a converting Boeing 747 which housed the power supply required for a megawatt class chemical oxygen iodine laser fitted in place of the aircraft nose cone, which you can see there. The aim of the OUT-1 was to act as a missile defense system, and in 2010 successfully destroyed 2 missiles during a test. Unfortunately, later in 2010, the project's funding was cut before it was eventually cancelled in 2011 at an estimated cost of over $5 billion. Any hopes for revival of this platform were quite literally scrapped in 2014, as all usable parts were stripped from the aircraft. More recent attempts have looked to integrate a laser onto UAVs, fighter jets, and attack helicopters alike. Next slide, please, Aaron. In the context of HGVs and other airborne objects, a space-based laser system is another possible solution. This could be a laser integrated with a satellite or spacecraft, which could provide space-to-space or space-to-Earth capability. An obvious advantage of having a laser in orbit is the lack of atmospheric effects on its emission, which in turn enables a much larger range of engagement. Due to the nature of orbit, and by having a space-based laser system at a considerably higher altitude, it enables a larger region to be covered or protected by a single entity. By having a laser in orbit above the operating envelope of HGVs, for example, this also presents the opportunity to illuminate surfaces on a target that may well be less protected by their inherent design. As with most space-based applications, whether it's laser-based or just other, there are significant costs involved, and there are inherent challenges with maintaining the power requirements of a space-based laser once in orbit. It is well documented how precarious launching a satellite or spacecraft can be. There is also an additional risk of releasing dangerous chemicals into the atmosphere if it was to fail on launch. On top of all this, a space-based laser could have implications on the Outer Space Treaty, which has an aim to prevent weaponizing space. Space-based laser system development is seemingly a lot more infrequent than the airborne equivalent, and there are currently no publicly known platforms in work. An example of a space-based laser system can be found in the 1986 Russian Polyus rocket project. The Polyus rocket contained a megawatt-class carbon dioxide laser with the objective of taking out US anti-missile shields. This was an ambitious project that was completed in around 12 months. However, the rocket ultimately failed to reach orbit, and the project was cancelled a short time after. There are limited publications on other attempts at space-based laser platforms, but it's definitely an avenue that could be further explored in the future. I'll hand back to Aaron.
Brilliant, thank you. So as we draw this to a close, what are we shown? So our models show that heating by laser radiation can increase the heating on the thermal protection system, regardless of it being ablative or another method. So this shows potential cause for structural failure. However, the question on everybody's lips is, can a laser be effective for targeting and destroying a hypersonic glide vehicle? And the answer is, for a ground-based solution, probably not. The reason for this is the atmospheric propagation effects and these being severely range limiting for what is inherently a long-range issue. However, some potential mitigations were suggested by outfitting a laser on an airborne or space-based system, which could offer you a solution by physically placing you closer to the target. But further work and modelling would definitely need to be done to prove or disprove this statement. So with that being said, that draws us to a close, and I'd like to open up to any questions. Thank you very much for listening.